Hello everyone, I'm the presenter Chao-Ho from National Taiwan University, Taiwan. Today, I'm going to present our work, Low IR Drop Test Pattern Regeneration using a fast predictor. This work is supported by ANSYS. In any integrated circuit, there exists a voltage drop from the power supply to any instances. This is called IR drop. Excessive IR drop can result in malfunctions of circuits, so they must be avoided at all costs. This is a serious issue for modern technology nodes, particularly when it comes to circuit testing. There are three main reasons. First, power consumption and IR drop in test mode is usually larger than that in functional mode. As a result, a circuit that is correct in functional mode may fail in test mode, resulting in excessive yield loss. Second, every instance has different IR drop, and different test patterns have different IR drop distributions as well. The pictures are the IR drop map of B19 benchmark circuit when running in test mode with two different test patterns. The supply voltage is 0.95 volt. As you can see, these two maps are vastly different, and both of them have hotspots that IR drop almost reaches half the supply voltage. Third, modern ICs are complex. Traditional circuit simulation is no longer feasible for the industry. For example, B19 benchmark circuit has 350,000 cells. It takes 80 minutes to simulate the IR drop for one test pattern, and there are more than 1900 test patterns in total. That is, for this circuit, you need more than 3.5 months to simulate test mode and IR drop. We must find another way to tackle this serious problem instead of just focusing on traditional ways of circuit simulation. Previous works focused on low-power ATPG, in which they achieved some of their goals. But there were two major difficulties that rendered their works ineffective to reduce IR drop. First, the power metric like weighted switching activities and flip-flop toggle counts are not sufficiently accurate. Second, and most importantly, low power does not guarantee low IR drop at all. Take a look at the following example. In the left, every point denotes the test pattern. Pattern B and C have the same power measured by weighted switching activities. However, both their IR drop distribution and worst IR drop value, as shown in the IR drop maps in the right, can't be more different. Therefore, we have to target on low IR drop ATPG. We apply machine learning to predict IR drop by each instances in a circuit. Machine learning can speed up IR drop estimation by hundreds of times. We will show these results later. To sum up, there are three motivations of our work. First, excessive IR drop causes testing yield loss. Second, accurate IR drop analysis is time-consuming. Third, previous techniques, such as low-power ATPG, did not generate IR drop safe patterns as we want. The goal of our work is to generate IR drop safe patterns. We aim at no fault coverage loss, low test length overhead, and fast IR drop prediction. First, we proposed a method that used low IR drop preferred values for X-filling, an improvement from previous works that use low power preferred values. Second, we extract important bit assignments for speed up. I will explain this later in my presentation. Third, we applied machine learning for IR drop prediction. Our results shows that we achieved the goal of IR drop safe pattern generation. There are no predicted IR drop violation in our output test pattern set. There is also no fault coverage loss and only slight test length overhead at 2.37%. Introduce the previous works. The first research proposed a method for low-power ATPG by feeding don't care bits with low-power preferred values, which were obtained considering circuit structures. This work, as most earlier works in the field, only cares about power, so it doesn't generate IR drop safe patterns, as I have shown in the picture in the page 4. Nonetheless, their method is still modified and used in our work as low IR drop preferred value filling. I'll explain this later. The second one is the vector-based IR drop predictor proposed in work, shown as in the bottom of the slide. Vector-based dynamic IR drop prediction using machine learning in 2021. It can predict IR drop of each cell in different test patterns, which meets our needs. The prediction time is faster than IR drop simulation by hundreds of times. With this tool, estimating the IR drop distribution of each individual test pattern becomes feasible. As a result, we integrate this predictor into our flow, into our low IR drop test pattern generation algorithm. We will call it IR drop predictor later on in our presentation. Next, I will introduce the proposed techniques. This is the overall flow of our work. We will call it regeneration loop later on. The input data include the test circuit and its test patterns generated by Synopsys TetraMax. The output is IR drop safe test patterns. First, we obtain the IR drop of each cells of a test pattern by the machine learning-based predictor. It is pre-trained. After getting the predicted IR drop, we remove IR risky patterns, that is, patterns with predicted IR drop violation. But before this operation, if we are not in the first iteration and the maximum care bit ratio of regenerated test patterns is extremely low, we perform important bit assignment extraction, or IBA extraction. I'll explain this later. After that, we call these test patterns IR drop safe patterns. We then check whether removing IR drop risky patterns results in the loss of fault coverage. If the answer is not, these patterns are the final output. Otherwise, we continue the regeneration loop. Then, if we're in the first iteration, or there are new important bit assignments, we have to do first pattern analysis and then perform low IR drop ATPG. Otherwise, we directly go through low IR drop ATPG. In this step, we regenerate test patterns to recover the fault coverage loss by removing IR drop risky patterns. Then we go back to the start of the loop to input regenerated patterns to the IR drop predictor. The simplified data flow of our work. Different from the previous slides, pattern analysis is shown as the first operation of the data flow, since important bit assignment extraction is not performed in the first iteration. However, both low IR drop ATPG and pattern analysis is dependent on the result of IBA. First, I will introduce important bit assignment extraction. The goal of IBA extraction is to categorize test vectors and fill them with their respective better fitted preferred values. First, we categorize test patterns into two pattern sets, IR drop safe and IR drop risky patterns. We then calculate scores S0 and S1 as shown in the slides. As you can see, the score is defined as the difference of numbers of IR drop risky patterns and IR drop safe patterns with bit I equals 0 or bit I equals 1. The largest of all these scores is our important bit assignment, or IBA. We only choose one bit as IBA in our experiment. In this example, there are 8 regenerated patterns, 4 IR drop safe and 4 IR drop risky. The maximum care bit ratio is 20%. Most of these bits in test patterns is don't care bits. They are to be filled in low power filling later on. There are 2 IR risky patterns with bit 1 equals 0, so N0 risky of bit 1 is 2. There are 0 IR safe patterns with bit 1 equals 0, so N0 safe of bit 1 equals 0. We then calculate S0 of bit 1 is 2 minus 0 equals 2. Similarly, we calculate S1 of bit 1 is 0. After calculating all of these scores, we find that S0 of bit 1 is the largest among them. So bit 1 equals 0 is the important bit assignment. Let me introduce pattern analysis. Is to generate low IR drop preferred values. We only do this in the first iteration or after IBA extraction. If it's the first iteration, we select 5% of test patterns with the lowest IR drop as low IR drop patterns. If it's after IBA, we first filter these patterns by IBA, then select the safest 5% of test patterns as low IR drop patterns. Then, we determine preferred values by comparing N0 and N1 values, defined as the number of zeros and ones for a given bit. If there are more ones than zeros for bit I among these patterns, the preferred value for bit I is 1, and vice versa. I'll show you an example in the next slide. In this example, there are 80 IR drop safe patterns, so we take safest 4 patterns for this operation. There are 3 ones and 1 zero for bit 1, and 3 zeros for 1 1 for bit 3, so the preferred value of bit 1 is 1 and bit 3 is 0, respectively. Introduce low IR drop ATPG. So, there is an operation called IR drop unsafe pattern removal. Removing patterns can result in a loss of fault coverage, so we use low IR drop ATPG to recover fault coverage to the initial percentage. First, we perform partially specified ATPG without exfilling by commercial tool. Then, we separate test patterns into 2 groups by important bit assignments. For example, if the important bit assignment is bit 1 equals 0, patterns with bit 1 equals 0 is one group, and patterns with bit 1 equals 1 or don't care is another group. Next, we perform constraint static test compression for each of the 2 groups. We limit care bit ratio since the second iteration. Finally, we fill in the low IR drop preferred value as we have computed. In step 1, we regenerate 4 partially specified patterns. In step 2, we group them by IBA. In this case, it is bit 1 equals 0. Patterns with bit 1 equals 0 are in group B, and patterns with bit 1 equals 1 or don't care are in group A. In step 3, due to maximum care bit ratio limit set at 50%, group B is not compressed because after compression, the pattern should be 0, 1, 1, don't care, and the care bit ratio would be 60%, which is larger than our restriction. Finally, patterns in each of the groups are filled in their respective preferred values. I'll introduce our experimental results. Setup. We use 45 nanometer process with 0.95 volt supply voltage. We have 3 ATPG modes: power unaware, power aware, and our low IR drop mode. All modes of ATPG are performed by Synopsys Tetramax. The parameter of our circuit and machine learning results. As you can see, the IR drop predictor can speed up IR analysis by hundreds of times, which is the most crucial part to enabling our pattern regeneration algorithm. The error of the predicted IR drop compared to Red Hawk SC simulation results are also acceptable. Take B19 for example. The IR drop of the final test pattern set are mostly in a range of 0.23 volt to 0.32 volt. This means that we can keep the mean IR drop prediction error below 10%. The original pattern contains 400 IR drop risky patterns. After the first iteration, the number of risky patterns dropped to 35, showing that our low IR drop pattern generation works very effectively. The objective of our work is to generate IR safe patterns. IR drop violations are not allowed in the final results. These two figures shows the IR drop of initial and final test patterns. You can see our claims are verified. This is the result of important bit assignment. It successfully reduced the number of regenerated IR drop risky patterns. As our overall flow shows, if there are no risky patterns to be removed, the regeneration procedure is completed. Therefore, important bit assignment can really reduce the runtime of our procedure. In the following slides, I will show three tables for comparison of the three ATPG methods. This table shows the test length and fault coverage comparison. Our work only has 2.37 of the test length overhead, while not sacrificing any fault coverage compared to power-unaware ATPG by commercial tools. And our work even performs better on both test length and fault coverage compared to power-aware ATPG by commercial tools. Statistics. Our total runtime are longer than both power-aware and power-unaware ATPG by commercial tools by tens of times. However, most of our runtime is on IR prediction, and the runtime of pattern generation is roughly on par with commercial tools. This table shows the comparison of number of IR risky patterns. IR violation threshold is 1/3 of VDD. There are no IR drop violations in our final pattern set, since it's the primary goal and requirement of our work. Both power-unaware and power-aware ATPG by commercial tools fail to generate IR-safe patterns. Surprisingly, power-aware method even has worse performance than power-unaware one for B19 circuit. I'll show some charts to explain this result. Two charts shows correlations between real IR drop analyzed by Red Hawk SC, our predicted IR drop, and the power metric used in commercial tools, that is, flip-flop toggle count. As you can see, flip-flop toggle count is an extremely bad predictor for real IR drop, while our predicted IR drop is much more highly correlated to Red Hawk simulated IR drop. This explains why power-aware ATPG has even worse performance for B19 circuits. To conclude our work, we proposed and implemented a low IR drop test pattern generation algorithm and successfully generated IR drop safe test patterns. We applied machine learning to speed up IR drop prediction by hundreds of times. In our flow, we utilized low IR drop preferred value filling and performed important bit assignment extraction. We achieved the goal of zero IR drop violations for all test patterns, while boasting no fault coverage loss and keeping the test length overhead to the minimum. This is the end of my presentation.